Hello, good evening, everyone, and welcome you all to uh, week 2 tutorial of applied thermodynamics. I am Tharanga Sutia, and wait for a couple of minutes for others to join. And in between that, let me share the screen. Okay. So let us start today's class. So in today's class, we will be basically dealing with steam power cycles. I will first of all give you an overall idea of uh, what is a steam power cycle, how does it operates, and what are the different components, and then we will do numericals, very basic numericals related to the components, because I have seen that in the week 2 the advanced questions like the reheat, regenerative, these all parts have not been taught. So the basic questions will we will be doing this in this week's tutorial. So what is steam power cycle? So a steam power cycle is a power cycle is a power producing cycle in which the working fluid is steam. Okay, so in the last class we have discussed about, like, from a high temperature source to a low temperature sink, we can input one engine that will produce some work, and by taking some amount of heat Q1 from the high heat reservoir and rejecting some amount of heat Q2 to the low heat reservoir. Okay, so this part is basically what we are going to study now. This cycle, what are the different types of cycles that we are going to study. So this is basically a power producing cycle. Okay, and this power producing cycles, based on the working fluid that we use, can be of two types. One is vapor power cycle, and one is gas power cycle. Okay, so what is vapor power cycle is just that is what we call it in simple language is basically what we call it as a steam power cycle. Okay, so this is the basic thing. Like in the last class we dealt with the second law of thermodynamics, and we understood that if we have to take out heat and we have to produce some amount of work, then we will have to reject some amount of heat to another low temperature sink, and in doing so we will be operating an engine, and basically this engine part is what we are going to study, and which requires one power producing cycle, and this power producing cycles can be of two types, like vapor power cycle and gas power cycle, and today we will be dealing one of the vapor power cycle, and that is basically the steam power cycle. Okay. Fine. So now then let us see what are basically the different components of the vapor power cycle, or what we call is as the steam power cycle. Okay, so in a steam power cycle, let me start from the very beginning. Okay, so the one that what you can see this TH, okay, what you are looking this TH, that is from where the heat is extracted, is basically the boiler component. Okay, so there will be one boiler where some coil or some amount of heat is taken. Okay, let's say Q1, this is what I denote it as. So that heat, it is given either by burning of the coil or by whatever process you put some amount of heat, where in this boiler the water is converted into steam. And okay, and after leaving this steam, what happens, this steam enters a turbine. Okay, and now it directly doesn't enter, it has some other parts also, like the nozzles and all, where which will be helpful in like increasing the speed of the steam exit before entering the turbine. So this will it will go and strike on the turbine blades, and it will rotate the turbine, and this shaft is now it can be attached, it is attached to some amount of what you call some amount of alternators, and in that it will be used in producing that amount of work. Okay, so some amount of work that what we already studied, this WT amount of work is basically produced by let me use different color so that you don't get confused here. Okay, yeah, so Q1 WT amount of work is taken out. Okay, then what happens after this now after that what happens now, according to second law of thermodynamics, we cannot do this type of work until and unless there is some amount of heat rejection. So how this heat rejection is done now, after the steam comes out, we will pass this steam through a condenser. Okay, this condenser is nothing but basically it is an heat exchanger. Okay, in this condenser what happens, Q2 amount of heat gets rejected. Okay, some Q2 amount of heat gets rejected, and this is basically your condenser. And after this condenser, what happens, it enters a pump. Okay, so it enters a pump, and from this pump and since this is a pump, so this will be basically a work consuming device. Okay, so some amount of work WP will be done here, but I will discuss it in great details, like what sort of work or how this can be increased or decreased, and then this cycle will be getting repeated. Okay, so this is basically what is the schematic diagram of a steam power cycle. So this B is basically stands for boiler. Okay, and what is the work of the boiler, where water is getting converted to steam by taking Q1 heat. Now how this Q1 heat is taken, whether it is taken by burning coil or whether it is given by any whatever source, this is not important to us. When we will do such questions, it will be important, but right now this is an overall, some Q1 amount of heat is taken in order to vaporize the water and produce the steam. Okay, T, this basically stands for the turbine. Okay, this will be the one that will be basically producing the work. So this is where WT amount of work is produced. Fine. Then after that, that condenser, this basically there is this condenser. So this condenser is, this stands for the condenser. So this is where what steam gets condensed to water by removing or releasing Q2 amount of heat. Okay, and last but not the least, pump what it does, because in order to run this process, you'll see it later on. In order to run this process, the condenser, now what happens after the exit of the condenser, the pressure decreases, the steam pressure decreases. So this pump, what it does, it brings the steam pressure okay, let me write in another place. So what pump does, it brings the pressure of the steam coming out of condenser to the boiler pressure. Okay, so that the entire cycle gets completed. Okay, so what it does, it basically brings back. So how this basically rotates, it rotates in this clockwise direction. Okay, so that is basically the work producing device. Okay, and brings back to the original pressure by consuming WP amount of work. Okay, now then there are some parameters which we should understand in order to solve different problems related to this particular thing. Okay, so the first parameter that basically we have to evaluate the performance of the cycle, like how good is the cycle. So in order to evaluate the performance of the cycle, what we have to do, we have to calculate certain parameters or certain indices. So one of these indices is ideal cycle efficiency. Okay, so we all know what is efficiency. Efficiency is basically desired output by input. Okay, so this is basically efficiency. Now this efficiency is of three types, like ideal cycle efficiency. So in this ideal cycle efficiency, what happens when all the processes involved in when all the processes involved in the cycle are taken to be reversible. Okay, if you take all the processes in the cycle that combine, all the processes combined to make the cycle, if you take them as reversible, then this becomes, and the efficiency, the corresponding, the efficiency of the cycle is called ideal cycle efficiency. Okay, and we know that in reality no any cycle can be ideal, because there are always reversibilities. But why we require the ideal cycle efficiency? Because this will give us the maximum limit, or we will know the whether the actual cycle is it feasible or not. That means it will give us a bound to the maximum limitation of the efficiency of the cycle. Okay, the second thing is your actual cycle efficiency. Okay, what we will do here in this case, uh, because of some irreversibilities present in the cycle, the calculated efficiency will become actual cycle efficiency. Okay, then the third part is what is relative efficiency. Okay, the third part is what is basically your relative efficiency, and relative efficiency is nothing but the ratio of ideal cycle efficiency to the actual cycle efficiency. Okay, so it is the ratio of the ideal cycle efficiency to the ratio of the actual cycle efficiency. So then the next is your work ratio. Okay, so this is your work ratio is W net divided by W turbine. Okay, it is the ratio of net work output, it is the ratio of net work output to the positive work. Fine. Okay, next is your back work ratio. Okay, so back work ratio is WP divided by WT, that is ratio of positive work to the negative work. Okay, so back work ratio. Now then we can establish a relationship between work ratio RW and back work ratio, that is RBW. Okay, so what we know that RW is basically W net by WT. Now if you remember, this W net will be nothing but WT minus WP divided by WT. Okay, and this one I can write as 1 minus WP by WT, which is nothing but 1 minus RBW. So the relation is what? The relation is basically RW is equals to 1 minus RBW. So higher so what we can write is that higher the back work ratio, lower is the work ratio, and lower will be the cycle efficiency. Okay, fine. Next is your specific steam consumption, or you can say it as SSC. Okay, next is your specific steam consumption. So what is this? It is basically the mass flow rate of the steam per kilowatt hour power produced by the cycle. Okay, so what is basically the expression for SSC is nothing but 1 by W net. So this will be your kg per kilojoule. Okay, and this one I can write as 1 by W net kg per kilowatt into seconds. Okay, and this one if you have to write kg per kilowatt hour, so this will be your 3600 kg by W net by W net kg by kilowatt hour. Okay, so this is your expression for specific steam consumption. Okay, so we will be calculating these all parameters today. Okay, now let's look at the Carnot vapor cycle. That means we know that in Carnot cycle there are two reversible adiabatic processes, and there are two reversible isothermal processes. Okay, so in Carnot vapor in Carnot cycle we know that there are two reversible. So this just we will apply in case when our fluid is basically a vapor. So when it is basically a vapor, or say it is a mixture of steam and water, that is liquid water, so there will be this dome shape. What is this dome shape is basically indicates is that this line is basically your saturated vapor line. Okay, and let me use blue for liquid. I like the color blue for liquid. So this is basically your saturated liquid line. Okay, so and in between this it is basically a mixture of, let me use another color. So it is basically here it is mixture of liquid and vapor. Okay, so that means this side, whatever in the red region, it is basically the vapor region. Okay, and this blue region is basically your liquid region. Okay, and this green region is basically your mixture of both liquid, and this point where it intersects is basically your critical point. Okay, so this is your critical point. Okay, so now here in such particular situations when it will be a mixture of two phases at a time, how will the Carnot cycle look, that we are going to see. Okay, how will the Carnot cycle look, that we are going to see. Okay, fine. So this is a TS diagram. So the two isothermal processes will be these two processes will be isothermal processes. Okay, I am drawing two constant temperature lines, and there will be one isentropic process, because a reversible adiabatic process is basically an isentropic process, so it will be basically a straight line also. Okay, so now if I name this as 1 I name this as 2, I name this as 3, and I name this as 4. Okay, so then this will be my TH and this will be my TL. So what will be this one? This part will be basically my WP, this part will be basically my W, this part will be basically my WT. Okay, and this part will be basically my Q1, and this part will be basically my Q2. Okay, so then Q1 is basically nothing but H3 minus H2. Forget about how it came, we will derive after some time. And WT will be basically H3 minus H4. Q2 will be your H4 minus H1. Okay, sorry, H1 minus H4, whatever, H4, just a negative sign will be there. And WP will be basically your H2 minus H1. Okay, fine. I've removed all the negativities here. I'm just putting all these positive terminals. Okay, and you know that it will be negative positive. Okay, fine, I'm putting it as it is. Okay, I'm putting it as this, so this will be basically your H1 minus H2. Okay, and this will be H4 minus H2. Okay, so then what we can do is that we can calculate the eta Carnot. Okay, so that will be W net by Q1. W net is nothing but Q1 minus Q2 by Q1. Okay, now you've put it this all terminologies here. H3 minus H2 minus H4 minus H1. Okay, divided by H3 minus H2. Okay, so then you will get here 1 minus H4 minus H1 divided by H3 minus H2. Okay, and that will be nothing but 1 minus Q2 by Q1. And since this is a Carnot, that means all the processes are reversible. This is actually equals to 1 minus TL divided by TH. Okay, fine. Now let us look. So this is the but in actual case what happens, we do not run our steam power cycle on Carnot cycle. Why? Because there are drawbacks of this Carnot cycle. The first drawback is that due to partial condensation of steam in the condenser, it is difficult to design such a condenser. Okay, so that means what? You can see here at the exit point, that is the point number 1. Okay, at the point number 1, at this point basically, okay, this point is in between this saturated liquid, and this is basically a mixture of both liquid and vapor. Now when should we stop? How can you say to the condenser that please stop whenever you reach at this particular quality of the steam? Okay, so this is very difficult to design. So this is one drawback of the Carnot vapor cycle. Now the other thing, suppose by some process you have made it to stop it here. Now this mixture of vapor and liquid cannot be pumped to a high pressure by means of pump. you will require a compressor to bring back to the boiler pressure. You will require a compressor to bring back to the boiler pressure, which means high power consumption. Okay, which means it requires very high power consumption. Okay, and the third one you can see here, that you can see here at the exit point, that is the point number 4, it is also a mixture of both liquid and the vapor. So that means that when it is inside the turbine blades, it is running inside the turbine blades also, it is a mixture of both liquid and the vapor. Now the turbine, it is designed to run on vapor. If you put that water or so, it will basically damage the turbine blades. So what will happen, because of the quality of steam at the exit of turbine, there can be damage of turbine blades. Okay, so these are basically the drawbacks of the Carnot vapor cycle. Now since these drawbacks are there, so we have to introduce this Rankine cycle in order to run our steam power cycle. So once again, let me draw the schematic diagram. Okay, so there is this turbine here, then from this turbine this comes this condenser. Okay, and from this condenser, instead of a compressor, we will just put a pump here. Okay, fine, and we can draw the TS diagram also. Okay, now this heat addition, instead of okay, so this is Q1, this is WT, this is Q2, and this is WP. Okay, so what happens here, what are the different processes? The processes are two reversible adiabatic process. Okay, the processes are, okay, if I name this okay, so if I name this pump 2 here is basically 1, and this is 2, and this is 3, and then this is 4. Okay, so the two reversible adiabatic processes are basically 1 to 2 and your 3 to 4. Okay, and constant pressure heat addition. What is the constant pressure heat addition process? That is basically the process 2 to 3, and constant pressure heat rejection. Okay, and the constant pressure heat rejection process is basically the process 4 to 1. So now since the constant pressure heat addition, and so the constant pressure lines basically looks like this in case of your TS diagram. Okay, so the constant pressure lines looks like this. Okay, so now since this is a pump, okay, you are using pump here, so the pump can only operate when it is fully liquid. So let me take one ideal situation when your exit of the condenser is basically a saturated liquid. Okay, so that means this will be my point 1, and then from here it will be compressed isentropically to the point 2, and from here to here this is basically my boiler heat addition is taking place, and then from 3 to 4 it is basically my expansion is taking place. Okay, so this is your TS diagram of a simple uh, Rankine cycle. That is basically your ideal Rankine cycle. Now again, I'm telling this as ideal because of the fact is that we have not include any types of irreversibilities here, but the irreversibilities can also be removed. Irreversibilities are always present, and such type of questions we will be doing in the next class. Okay, now a couple of questions we will do off from this, but before that, let me tell you one more thing is that so if suppose this process, like how if you increase the boiler pressure, if you increase the condenser pressure, what will be basically the role of the boiler and the condenser pressure, such type of things will also come into know. So okay, now let us then, hello, hello. Okay, sorry, there was a network interruption from my side. Okay, and okay, so now uh, let us move. What I said is that in an ideal Rankine cycle, that is basically there are two reversible adiabatic processes, as in the case of an Carnot cycle, and there is one constant pressure heat addition process that it happens in case of the boiler, and there is one constant pressure heat rejection process, that is basically the process of your condenser, that is the process from 4 to 1. Okay, so now let us do the questions related to whatever topics that I have discussed. Now the first question is, why is the efficiency of a Rankine ideal Rankine cycle is less than that of the ideal Carnot cycle? Okay, so let us first draw the Carnot cycle. Okay, so this is your TH and this is your TL. Okay, 1 2 3 and then 4. Okay, and here your eta Carnot, what we have got is basically equals to 1 minus TL divided by TH. Okay, next let us draw for this Rankine cycle. Okay, remember these are constant pressure lines. Okay, okay, so now the if, because here in this case now this temperature, it is basically the constant, that is, say this is the, equal to the original TL value. Okay, now here there are two temperatures. This is basically your TH1 and there's one more temperature, this is basically your TH2, and there are so many other temperatures in between these two. So in this case, what will be my TH? So what we can take is that we can take a mean temperature of heat addition, say this is some TH mean. Okay, so if you see, then here the your eta Rankine will basically become 1 minus TL upon TH mean. Okay, now if we are looking for the same for the same for the same maximum and minimum temperature of the cycle. Okay, that means what is the maximum temperature here? This is TH1. Okay, and what is the maximum temperature here? Basically TH. So what it suggests is that this means that this implies TH1 is equals to your TH. Okay, and we know that the minimum temperature for both the cycles is TL, so that is same. Okay, so for the same maximum and minimum temperatures, let me color it in different and you'll understand probably more. Yes, TH1 is basically equals to TL, and this TL is equals to your black TL, that is my Carnot cycle and my Rankine cycle is. So for the maximum temp, same this one. Now this will now depend basically on, now from this figure we can see that TH mean is less than TH. Okay, so therefore the eta Rankine is less than eta Carnot for the same maximum temperature for the same maximum and minimum temperature of the cycle. Okay, fine, no doubt I think in this particular question. So what we did basically, we have calculated the efficiency, and because we are considering both as ideal, so we can express the efficiencies in terms of the ratio of certain temperatures. Okay, so now, and then we have seen that for the same maximum and minimum temperatures of the cycle, the eta Rankine is basically less than the eta Carnot. Okay, next is, when the temperature of the condenser increases for a simple Rankine cycle, the net work produced by the cycle 1 increases, second decreases, and does not change. Okay, so this is a simple Rankine cycle. Okay, and this is my condition 1, 2, 3, and say 4. Okay, so now my W net is basically WT WP. So W net is basically my WT minus WP. Okay, and normally what happens, WT is far greater than WP, so therefore W net is approximately equals to, we consider this as WT. Okay, so the net work done is directly, you can correlate it, or it is directly proportional, or it is directly in link with the WT. That's what you can say. Okay, so now it is telling us that if the temperature of the condenser increases, now in this case my temperature of the condenser is, for my case 1, this is my TL1. Okay, now suppose I have increased this temperature to here. Okay, the rest all the process are same, so this becomes my 1 dash and this becomes my 4 dash. Okay, this becomes my 4 dash, and this temperature is now my TL2. What will happen in this case? So in this case also I will get some work produced, and that is my WT dash, and I will also get some amount of P, that is my WP dash. Okay, so for the case 1, my WT will be what? H3 minus H4. Okay, and for my case 2, my WT is equals to H3 minus H4 dash. Okay, WT dash. Now clearly WT dash is less than WT. Why? Because this gap, you can see this gap. This gap is basically your WT, and this gap is your WT dash. Okay, so WT dash is less than WT, therefore W net decreases as we increase the condenser temperature, therefore our answer will be decreases. Okay. If you have any doubt, you can ask. Okay. Okay, so let us move to the next question. A turbine operating under steady flow conditions receives steam at the following state: pressure 13.8 bar, specific volume 0.140 meter cube per kg, internal energy is this, velocity is this, and the state leaving the turbine is this one, pressure this one. So basically in the steam power plant, now you forget about all the components, you just look at the turbine. Okay, this is the inlet to the turbine and there is some exit to the turbine. Okay, just this thing we have to consider. The rest all things we should not consider. So okay, now I'm giving this state as state 1 and I'm giving this state as state 2. That means my 1 is my entry and my 2 is my exit. So what are the things that are given? That at the inlet stage my pressure P1 is equals to 13.8 bar. Okay, my specific volume V1 is equals to your 0.143 meter cube per kg. Okay, and my internal energy U1 is equals to 2590 kilojoule per kg, and my velocity C1 is your 30 meter per second. Okay, then the state of the steam leaving the turbine is basically P2. P2 is given as 0.35 bar. Okay, and my specific volume at the exit V2 is given as 4.37 meter cube per kg. Okay, and my internal energy at the exit is also given as 2360 kilojoule per kg, and my outlet velocity is also given, this one as 90 meters per second. Okay, then what it is given is that, okay, now in the other cases we have not considered. Now here there is some heat loss to the surroundings, they are telling you. Okay, and this heat loss is nothing but 0.25 kilojoule per second. Okay, and some amount of heat flow is there. Okay, this m dot, that the mass flow rate of the steam is given as 0.38 kg per second. So what are the things that is given as? Q dot is given as minus 0.25 kilojoule per second. So since minus is because the heat is getting rejected, and your mass flow rate of the steam is basically given as 0.25 kilojoule per second. Okay, so these are basically your given parameters. Oh, I'm sorry, 0.38. Okay, so then we have to calculate what is the power work produced by the turbine. I'll give you 1 or 2 minutes to solve, and then I will solve the question. Okay, so how should we proceed? Now this is an open system. Okay, what it is? It is an open system. Okay, and secondly, steady flow. Okay, steady flow. So what we will apply here? Applying steady flow energy equation. Okay, so if I take this blue dashed part as my control volume, okay, this blue dashed part as my control volume, so in this case what I can write this as d e c v by dt is equal to q dot minus w dot plus m1 dot h1 plus c1 squared by 2 plus g z1 minus m2 dot h2 plus c2 squared by 2 plus z z2. Okay, now since it is steady flow, so this part will be equals to 0, and we know that m1 dot is equals to m2 dot is equals to m dot here, because this is one inlet and one outlet. Okay, so therefore our equation now reduces to w dot is basically equals to q dot plus m dot times h1 minus h2 plus c1 squared minus c2 squared by 2 plus z of z1 minus z2. Okay, now since there is no potential energy change is given, so this part will also be equal to 0. So finally what will be my equation? My equation will be w dot is equals to q dot plus m dot times h1 minus h2 plus c1 squared minus c2 squared by 2. Okay, now h is not given to us directly. Okay, q is given to us, m dot is given to us, c1 and c2 is given to us, h is not given to us, but u and pv are given to us. Now since h equals to u plus pv, okay, so using this equation, now finally what we will get is w dot is nothing but that is equals to q dot plus m dot times u1 plus p1 v1 minus u2 minus p2 v2 plus c1 squared minus c2 squared by 2. Okay, just put the values. So this one also I think I can bring to a more finer term, plus okay, so q dot is given as minus 0.25 kilojoule per second, is basically kilowatt, and your m dot is given as 0.38, this should be kg per second, I'm sorry, 0.38. okay, next is your u1 minus u2, 2590 minus 2360, okay, then your P1 V1, okay, 13.8 into 10 square, V1 is your 0.143 minus P2 is your 0.35 into 10 square into 4.37 okay, plus C1 squared 30 square minus 90 square by 2. Okay, so this is minus 0.25 plus 0.38 230 plus 44.39 plus so there should be 1000 also here. Okay, one hundred and 2.65 kilowatt. So this is basically the power that is produced by the turbine. Okay, so read the next question, try to solve. In between, then if you have any doubt you can ask me. Okay, so next is your at steady state a steam turbine produces 1050 megawatt by letting the pressure down from 50 bar to 1 bar. Superheated steam enters the turbine at 320 degrees Celsius with a velocity of 8 meter per second and the mass flow rate as 150 kg per minute. The steam leaves the turbine with a quality of 0.94 and the velocity of 65 meters per second. Determine the rate of heat loss from the turbine to the surroundings in kilowatt for superheated steam. Okay, so these are the steam table values are given. So again the same condition here. Now a little bit of complicated, like the things of that steam table things will come into picture. So this is basically the turbine here. Okay, so this is the inlet and again this is the outlet. Okay, forget about all other components that is present in this steam power cycle. We are now right now only focused on the we are just now focused on the component that is the turbine. Okay, so what it is telling is that the steam turbine that basically produces some amount of work, WT or W dot, what we have basically introduced. So basically we'll put this one only, is basically 1050 megawatt. Okay, so W dot produced is 1050 megawatt. Okay, and P1 pressure is 50 bar and your P2 pressure is your 1 bar. Okay, now what it is telling is that at this state 1, this is basically your superheated state. Okay, so that means in steam table you have to look for the values at for the values of the superheated steam. Okay, and what it is telling us that the temperature is T1 is 320 degrees Celsius. Okay, and its velocity C1 is your 8 meter per second. Okay, and the mass flow rate, just like the previous case, the mass flow rate, that is the m dot, is given to us as 150 kg per minute. Okay, then next is the steam leaves the turbine with a quality of 0.94. Now what this actually means? Okay, this actually means is that now what we are interested, from some superheated state to this particular state. Okay, so that is what, this is the point 1 and this is the point 2. This is what is going on, and here the exit is some quality, and here the x, that is the dryness fraction x, is basically your 0.94. that is what it is given to us. Okay, that this thing is basically given to us. Okay, so what it is telling us that x2, that is the dryness fraction at the point 2, is basically your 0.94, and your velocity C2 is given as 65 meters per second. Okay, now determine the rate of heat loss from the turbine to the surroundings in kilowatts. Okay, so you have to determine Q dot. Fine, these are the questions. Now values from the steam table are given to us, that what things are given to us from steam table. Okay, at 50 bar, 320 degrees Celsius. Okay, what it is given, H is equals to 2986.2 kilojoule per kg. That means at this point corresponds to this one. Okay, next what it is given to us, that at 1 bar, okay, your HF is equals to 417.50 kilojoule per kg, and your Hg is 2674.95 kilojoule per kg. Okay, fine. So therefore what we know, H1 is your nothing but this point, and this point is basically your this point. So H1 is nothing but 2986.2 2986.2 kilojoule per kg. Okay, this is your H1. Now how will we get H2? Okay, so H2, this point has got some dryness fraction, so H2 is nothing but HF at P2 plus X2 times HFG at P2. This can also be written as HF at P2 plus HG at P2 minus HF at P2 times X2. Okay, so what I can write this one is HF at P2 is what? 407.50. X2 is your 0.94. HG is your 2674.95 minus 417.50. Okay, so this is your 2539.503 kilojoule per kg. So I have got H1, I have got H2. Okay, I have got C1, I have got C2, and so now I can apply steady flow energy equation. What will we get? DECV by dt is basically Q dot minus W dot plus M1 dot H1 plus C1 squared by 2 plus Z1 minus M2 dot H2 plus C2 squared by 2 plus ZZ2. Okay, and from here what I can write this as DECV upon, okay, so this will be your 0 because this is a steady flow process. So from here what we have to calculate is basically the Q dot, so I will put the Q dot to the other side. This will be equal to W minus M dot times H1 minus H2 plus C1 squared minus C2 squared by 2 plus Z1 minus Z2. Now neglecting the changes in the potential energy as 0, what we can write this as Q dot is equals to W dot minus M dot times H1 minus H2 plus C1 squared minus C2 squared by 2. Okay, into 1000 I am doing this in order to convert this everything into kilojoule. Okay, so that I will do later, sorry, fine, after putting this numbers to. So what is W dot here? W dot is the work produced, and work produced is positive, so that is 1050 megawatt. 1050 into 10 to the power 3. Okay, so that is your megawatt, so I am converting this into kilowatt. M dot is your 150 by 60. Kg per second. Okay, and H1 is 2896.2, sorry, 2986.2 minus your H2 is 2539 2539.503. okay, plus C1 squared, 8 squared minus 65 squared divided by 2000 to make this one as kilojoule. 1050 into 10 to the power 3 minus 150 by 60 times, what is this? This is 446.697 plus, obviously this will be in minus sign, 2.0805. Okay, sorry, this is question is wrong, this is kilowatt. Okay, so here is kilowatt. 1050 minus 1111.54, 61.54 kilowatt. Next is what? A pump steadily draws water from a pond at a volumetric flow rate of 833 liters per minute through a pipe having a diameter of 127 millimeter diameter inlet. Water is delivered through a hose terminated by a converging nozzle. The nozzle has an exit diameter of 25.4, okay, and is located at 10.5 meter above the pipe inlet. Water enters at 20 degrees Celsius 1 bar and exits with no significant change in temperature and pressure. The magnitude of the rate of heat transfer from the pump to the surrounding is 5% of the power input. The acceleration due to gravity is 9.8 meters per second. Okay, so what it is telling is that basically if this is the pump, okay, this is the entry point, the exit point is it delivers through a nozzle, and this nozzle, this has some exit and this is some entry. So this is my point 1 and this is basically my point 2. Okay, and these two are separated by a height of 10.7 meter. Okay, so there is a height of 10.7 meter. Fine. Now what it is telling is that the inlet diameter d1 is equals to 127 millimeter. Okay, and the exit diameter d2 is 25.4 millimeter. Okay, so now if I will take z1 as equals to 0, so what will be my z2 will be basically 10.7 meter. Okay, my acceleration due to gravity g is 9.8 meters per second square. And one more thing is given to us is that the volumetric flow rate is equals to 833 liters per minute. Okay, this we can convert to meter cube or something like that. Okay, so in order to convert this to meter cube, 833 into 10 to the power minus 3 divided by 60, this will be your meter cube per second. Okay, now what it is asking us that the velocity of water at the inlet and at the exit. Okay, velocity of water at inlet. This is the first thing that it is being asked. Okay, so how to do? Volume flow rate is basically your area into velocity. Okay, now by conservation of mass, since m1 dot is equals to m2 dot. Okay, what is m1 dot? It is basically rho 1 a1 v1 sorry, so what I can write basically as rho 1 okay, volumetric flow rate. Now in this case we are operating underwater, so rho 1 and rho 2 are almost the same. So what happens, the v1 is equals to my v2, that is my volume flow rates are the same, and this is the same volume flow rate is there for the inlet and the outlet conditions. Okay, so the inlet and the outlet volume flow rate are the same. So if you have to find the velocity at the inlet, therefore inlet velocity c1 is equals to my volume flow rate divided by my a1. Okay, so c1 is equal to volume flow rate is if you solve this you will get 0.0138 meters cube per second. Okay, so this will be 0.0138 meter cube per second and pi by 4 times d1 squared, that is 0.127 whole square. Okay, from here this will be meter squared, so meters, this will be getting cancelled out, so finally you will get in meter per second. One 1.089 meters per second. Okay, then similarly you can get outlet velocity c2 is equals to volumetric flow rate divided by a2. Okay, so once again your c2 is equals to 0.0138 divided by pi by 4 times, is it 10.7 meter, no, 25.4 mm, so 0.0125 whole square. Okay, one 112.45 meters per second. Okay, so this answers the first part. Now the power required by the pump. Okay, so in the next case you will have to apply the steady flow energy equations again. Okay, power required by the pump. Okay, so applying steady flow energy equation, what you get here, dECV by dt is equals to q dot minus w dot plus m dot times h1 minus h2 plus c1 squared minus c2 squared by 2 plus z of z1 minus z2. Okay, now since no specific change in temperature and pressure, okay, and we know that reversible adiabatic work is basically equals to integration of VdP from 1 to 2, negative sign. So since there is no significant change in pressure and temperature, so this reversible adiabatic work will be basically equals to 0, or what you can say simply, this implies is that H1 is equals to your H2. So that means this term will get cancelled out. Since this is a steady flow equation, this term will get cancelled out. Now we know the volume flow rate, okay, and from the volume flow rate, can we calculate the mass flow rate? Yes, of course, we know the density of the water. Okay, so we know that rho is equals to mass per volume, or mass flow rate by volume flow rate. So from here the mass flow rate will be nothing but rho times the volume flow rate, and rho of the water is basically 1000 into volume flow rate, and what is your 0.0138, so it will be 13.8 kg per second. Okay, so putting all these values, and is there any heat loss is given? Yeah, one more thing it is telling to us is that, now let us write the steady flow energy equation once again. So that will be W dot is equals to Q dot plus M dot times C1 squared minus C2 squared by 2 plus Z of Z1 minus Z2. Now one more thing it is telling us that Q dot is equals to 5% of W dot, that means it is 0.05 of W dot. So what I can write this as, W dot is equals to 0.05 times W dot plus M dot times C1 squared minus C2 squared by 2 plus Z of Z1 minus Z2. Okay, so from here what I can write this as 0.95 W dot is equals to M dot times C1 squared minus C2 squared by 2 plus Z of Z1 minus Z2. Okay, now from here W dot is nothing but M dot is 13.8 by 0.95 times C1 squared, C1 1.089 minus C2 squared 112 point by 2000. Okay, because we required a power output in, we can write first in watt also, does not matter, because that's Z is your in meters. Okay, plus 9.81 times 0 minus 10.7. So this is approximately equal to 1274.4 kilowatt. Okay, so then let us move to the next question. Steam enters the condenser of a vapor power plant at 0.1 bar HF, where HF is this one, with a quality of the steam at 0.95. The condensate exits at 0.1 bar, and that is basically in the condenser what happens basically it's constant pressure heat rejection happens, and 45 degrees Celsius. Okay, so and the cooling water enters the condenser in a separate steam as liquid at 20 degrees Celsius, and it exists as 35 degrees Celsius with no change in pressure. Now heat transfer from outside the condenser and changes in the kinetic and potential energy of the flowing streams can be ignored. For the steady state operation, first of all you have to determine the ratio of the mass flow rate of the cooling water to the mass flow rate of the condensing steam. So what happens in the steam power plant? Now this is what the condenser looks like, isn't it? That's what we have drawn, if you remember. Okay, let me draw it once again here. Okay, if you remember that schematic diagram, this was the boiler, this was the turbine, this was the turbine, and from here this condenser was there, and then this pump was there. Okay, so this is what is this one. Okay, fine. So in this condenser now what happens, steam enters, this is the state 1, and then steam leaves, this is the state 2. Okay, and in doing so what happens, this steam is getting cooled. Okay, this steam is getting cooled and this steam is getting condensed, and it is losing heat. Now if it is losing heat, somebody should take this heat. Now that heat is taken by this circulating water. This heat is taken by this circulating water. Okay, this water will basically circulate. So this is your water in time, and water out. Okay, so what it is telling us that at the state 1, say if I'm naming this as state 3 and I'm naming this as state 4. Okay, this is steam in, steam in it is state 1, and steam out at state 2. Okay, so what it is telling us that P1 is equals to 0.1 bar, and we know that constant pressure heat rejection takes place, so P1 is equals to P2. Okay, and at 0.1 bar your HF is equals to 191.83 kilojoule per kg, and your Hg is 2584.7 kilojoule per kg. Okay, and what it is telling us that x1, that is the steam quality, is 0.95. so at this point what we can calculate, H1 is nothing but HF at P1 plus x1 times Hg at P1 minus HF at P1. Okay, what is HF at P1? 191.83 plus 0.95 times 2584.7 minus 191.83. Okay, so what I am getting it is H1 is equals to 252465.0565 kilojoule per kg. Okay, now then enters and condensate exits. Okay, and now what it is telling us, that the condensate, that is what it is basically exiting at 0.1 bar. So what it is telling us, that it is T2 is equals to your 45 degrees Celsius. Okay, and your H2 is your 188.45 kilojoule per kg. This is being told to us. Now next thing is, the cooling water enters the condenser in a separate stream. Okay, this both two streams do not mix with each other, and it enters at 20 degrees Celsius. Okay, so what it is telling us next is, T3 is 20 degrees Celsius. Okay, and your H3 is 83.92 kilojoule per kg, and T4 is given as 35 degrees Celsius, and H4 is given as 146.65 kilojoule per kg. Okay, now the first thing, ratio of mass flow rate of water to steam. Okay, so what we can write is that heat rejected by steam is equals to mass flow rate of the steam times H1 minus H2. Correct, no? Because whatever enthalpy it had in the entry, it will lose some enthalpy, and that is resulting in rejection of the heat. Now heat gained by water is basically what? Mass flow rate of the water times, it is gain. I'm already telling it's gain, so that means I have to make this term just positive, so this will be basically H4 minus H3. Correct? Now what it is telling us, it is telling us that heat transfer from the outside of the condenser is not at all taken into consideration. Okay, so heat transfer from outside the condenser is not taken into consideration. So for no heat transfer from outside and neglecting the Ke and Pe changes, what happens? Heat rejected by steam must be equal to heat gained by water. Okay, so now heat rejected by steam, heat gained by water. Okay, so now what we have to find out, we have to find the ratio of water to that of steam. So mw by m dot s is equals to h1 minus h2 by h4 minus h3. Okay, so what is h1? 2465.0565. What is h2? 188.45. that is H4 146.65 and 83 point. Okay, so this ratio is 36.29. okay, now next is energy transfer from the condensing steam to the cooling water, okay, per kg of the steam passing through. Okay, so energy transfer from heat to steam, from steam to water per kg steam. What will be this? This will be nothing but whatever Q divided by m dot. So that is basically your I can write this one as ms dot. So that is basically your h1 minus h2. And what is your h1? 2465.0565 minus 188.45. So this is 2276.6065 kilojoule per kg. Okay, fine. So let us come to the last question of today's tutorial session. So steam turbine receives a steam at a pressure of 20 bar and superheated to 88 degrees Celsius. The exhaust pressure is 0.07 bar and the expansion of the steam takes place isentropically. You have to calculate the heat rejected, heat supplied, net work done by turbine, thermal efficiency, theoretical steam consumption, these all things. Okay, so let us draw the TS diagram. So what is telling us that there are two pressures. This is basically your boiler pressure. Okay, this is equals to your this boiler pressure. This P is equals to equals to 20 bar. Okay, PB is equals to 20 bar. Okay, and then your condenser pressure is given to us. PC is equals to 0.07 bar. Okay, now what happens that your steam is now here superheated steam that is entering the steam. Okay, that is entering the turbine. Okay, so that is a superheated steam, and superheated steam is the degree of superheat is given to us as 88 degrees Celsius. So if I consider this as my point, this is my point 1. So what it is given to us that P1 is equals to 20 bar and T1 is equals to T saturation at 20 bar plus 88.6 degree Celsius. Fine, because this is given to us as the degree of superheat. Okay, now from the steam table you can see that this is equals to 212.4. So 212.4 plus 88.6 degrees Celsius. So this will give you your T1 is equals to 300 degrees Celsius. Okay, so this is the condition at which steam is entering. Steam is entering the turbine. Okay, then this steam is isentropically expanded to this point 2, then this is the point 3, and then this is the point 4. Okay, so now by using this we have to calculate heat rejected and blah blah blah, these all things. Okay, so now what are the values that are given to us? Yeah, you can see here, this is at 20 bar and 300 degrees Celsius. It is given to us that H1 is equals to 3024.2 kilojoule per kg, and your S1 is given as 6.7684 kilojoule per kg Kelvin. Okay, so this H1 and S1 is given to us. Now here at the point 2 we need to know the quality. Okay, so before that let us see what other things we can calculate from here. Yes, and what is your H3? H3 is HF at PC. Okay, that is the condensate pressure, and this is nothing but your 163.65 kilojoule per kg. Now how to calculate H2? H2 is nothing but HF at PC plus X2 times Hg at PC minus HF at PC. Okay, now how to know X2? How can I know X2? We know that S1 is equals to S2. Why? Because it is telling that isentropic. Okay, and what is my S1? My S1 is 6.7684. Now what is S2? S2 is nothing but SF at PC plus X2 times Sg at PC minus SF at PC. Okay, so from here 6.7684 is equals to SF at PC. What is my SF at PC? 0.55903 plus X2 times Sg is 7.7154, 0.55903. So from here I get X2 is equals to 0.87. So this is the quality of the steam at the turbine exit. Okay, so for therefore my H2 will be what? HF at PC 163.35 plus 0.87 times Hg is 2408.4 minus 163.35. Okay, so this is equals to 2116.54 kilojoule per kg. So I got H1, I got H2, I got H3. Okay, now how can I get H4? How can I get H4? Okay, so before that should I get H4? That is the first question. Okay, so what is the heat rejected then? Heat rejected is equals to your H2 minus H3. Okay, what is your H2? 2116.54, and what is your H3 is 163.65. Okay, so it's 1952.89 kilojoule per kg. That is your heat rejected, heat supplied. How will we calculate heat supply? So work done by pump will be equal to minus integration of VdP. Okay, now this pump process is from 3 to 4. Okay, so that means this will be Vf at Pc times P3 minus P4. Okay, and this Vf at Pc is 0.001 from the steam table, and this will be your 0.07 minus 20 into 10 to the power 3. Okay, so this will be your 1.993 kilojoule per kg. Okay, and this is nothing but this is equals okay, so then work done by the pump. So work done by turbine is what? H1 minus H2. Okay, so work done by turbine is H1 minus H2. What is H2? 2116.54. and what is H1? 3024.2. okay, kilojoule per kg. Okay, so this is the work done by the turbine, 3024.2 minus 2116.54. So it is 906.66. Okay, so therefore from thermodynamics cycle we know that summation of Q net is equals to summation of W net for a TD cycle. Okay, so W net, Q net is what? Q1 minus Q2, and this is what? WT minus WP. So therefore Q rejected is basically your Q1 minus WT plus WP. You put all these values, you will get Q rejected as 2859.487 kilojoule per kg. Sorry, Q added, I'm sorry. WT minus WP, you put all these values. So Q rejected we already have, so you will get Q1 is equals to WT minus WP plus Q2, that will be equal to 2859.487 kilojoule per kg. This is your heat supplied. So heat rejected done, heat supplied done, net work done. Net work done is equals to Wt minus Wp. And so net work done, you'll get the net work done as 932 137 kilojoule per kg. These all things we already have. Net work done by the turbine we have calculated. Now thermal efficiency, eta thermal is equals to Wt minus Wp upon Q1. Okay, so this you will get as 32.59%. Next is what? Theoretical steam consumption. Okay, SSC, that is what? 3600 by W net. Okay, kg per kilowatt hour. Okay, so this you will get as 3.86 kg per kilowatt hour. Okay, fine. So with this I will like to conclude today's class. Okay, we'll meet in the next class. Thank you.